So after we find the expression for the golden ratio, yeah. So last time we did this one. So how to find this number from this quadratic equation? Now we need to use this golden ratio constant to represent the formula for the Fibonacci numbers. And here the formula is like this. Yeah. So how to see it? So that's why I call it a magic formula. Yeah. Because it is very hard to connect Fibonacci numbers and golden ratio. How do you connect them? Right? Yeah. Not easy to see. What's the connection? Yeah. All right. So we need to understand. Yeah. So why? If we apply the Fibonacci formula, so here you can see the formula very strange. Yeah. First, let's look at the golden ratio first. Yeah. The golden ratio number, it looks like it's hard to see any special rules there, right? Yeah. So 1.618, so after 8, infinite many digits, and you cannot find any special rules. Yeah. No cycle, we know, yeah. So, many numbers, yeah. For example, 1/3 equals 0.33, infinitely many 3, repeat, okay? 1/7, like that, right? This is one cycle. After that, this cycle repeated. Second, and so on. Repeated, the cycles repeated, infinitely many times. Yeah. But this number, no similar cycle things there. Yeah. So the infinitely many digits, but without any cycle. Yeah. So the number in this way we call the irrational number. That's the irrational number. The numbers with cycles, rational number. Sorry. Rational number. Okay, that's the main difference. Yeah. So both rational numbers and irrational numbers together form the real numbers. Yeah. All right. And here we have our golden ratio is an irrational number. Yeah. Now we want to, but we know Fibonacci number is an integer. Here you use some irrational numbers. Root 5 is another irrational number, root 5. Okay. Yeah. So in this formula, you see many irrational numbers. Phi to the n, yeah, this term, the definite irrational numbers. Okay. Yeah. Minus 1, -1 to the n over phi to the n. Another irrational numbers. Then you do subtraction, then divided by root 5, then suddenly it becomes an integer. Yeah. So that's pretty strange, right? Yeah. So here, the first thing is we need to verify this formula is correct. How do you know that the formula is correct? Okay. Yeah. So first we need to verify it. Yeah. But verification means someone gives you the correct formula, but you need to use a special way to check if it is really correct. That's the verification. But someone gives you that formula first, right? Yeah. If nobody gives you the formula, you cannot do the verification, right? Because you do not have anything to be verified. Yeah. Yeah. So the next thing is, we cannot assume we have a formula to be verified. We have to discover the formula. Yeah. Because the formula like this, nobody can guess this formula, right? Nobody can guess in this special way. Too special. Yeah. So you have to find it. Yeah. Apply some from problem-solving techniques to find it. All right. So let's do these two things in part D, in our last lecture of this module. Yeah, we need to do these two things: verification and discover the formula. Yeah. All right. So that's the part C, the end of the part C. So now I need to jump to the part D. Okay. All right. Yeah. Okay. So let me bring up the part D. Here, part D. All right. Yeah. All right. All right. Yeah. So part D, we just do these two things. The first topic, the first part, verification of Fibonacci formula. All right. The question, how to verify it? Yeah. We need to use some smart method to do the verification. Yeah. Yeah. Because that formula, you can see, pretty complicated how to verify. Okay, yeah. So here, verify Fibonacci formula. All right, yeah. Yeah. Let me write this formula again. Yeah, all right. So we need some special tool to help us do the verification. Yeah. So that special tool, yeah, because you need to show it is true, this formula true for n equals 0, 1, 2, to infinity. Yeah. For any n greater or equal to 0. Yeah. Infinitely many cases. The question is, how do you verify a formula for infinitely many cases? Because nobody can exhaust infinitely many cases one by one, right? How can you exhaust infinitely many cases once a time? Yeah. Yeah. So you have to use some way, you can only do finitely many steps. You do your verification in finitely many times, but you can prove this formula is true for infinitely many cases. How to make that happen, right? Yeah. So that's the challenge part. Yeah. And here, so there is a very powerful mathematical tool we can apply here to do the verification. Mathematical induction. All right? That's your, discrete math topic. Yeah. So in your discrete math, so you studied this topic. Very powerful tool. So here we need to use this tool here to do the verification. So for the mathematical induction, there are some basic steps. Yeah. So here let me explain the basic steps. All right. Yeah. First, step one, we need to verify the base cases. Yeah. All right. So here, let me write the basic step. Yeah. So verify the base cases. Base cases. Yeah. Certain number of base cases. Sometimes one base case, but sometimes you need more than one. Yeah. Here we need two. We need to verify two base cases because look at here. There are two base cases. Another reason we need to verify two base cases. Look at in this recurrence relation. Yeah. On the right hand side, so there are two terms with consecutive subscripts. Yeah. So here, all these consecutive subscripts, but the right hand side, there are two lower terms. So that tells us we need to verify at least two base cases. That's the first step. Second step, we need to make induction assumption. Okay. Just make assumption. Okay. Yeah. All right. The step three. All right. Yeah. All right. Show that the statement is true for, so here, a lot of words. So I try to, do not say too much, because I will explain later. For, so here, here, let me just write n equals k plus 1, because explaining this k related, so you need in your, so make assumption. What's that assumption? Assumption true k, actually less than or equal to k. That's the assumption. So that k is in your induction assumption. Then you show the statement is really true when you extend the range that it is true. Because here in your assumption, the range is n less than or equal to k. But now you extend it. You extend it to n equals k plus 1. That's the key step. This step 3 is the most important step. After you complete these 3 steps, then you can say the whole statement is true for all non-negative integers n. Infinite many cases, always true. So the mathematical induction guarantees that final verification result. Okay, all right, yeah. So now we start our first verification, step 1, F0 verification. F0, you plug in N0 into this formula, so you get this expression. Yeah, any phi to the 0 is 1, right? Yeah. Any non-zero integer to the 0, yeah, non-zero, the base must be non-zero. Non-zero number to the 0 power 1. Okay, yeah. Also 1 here, 1 over 1, 1 minus 1, 0. Yeah. So our first verification, yeah, so it's correct. Okay, all right. Then second verification, yeah, F1, let's plug in n equals 1 here. Yeah, this time we need to use the specific value of golden ratio. The first step, we do not need to use the specific value, phi. Okay, yeah. Now we need to plug in the golden ratio number there. Yeah, then reciprocal. Yeah, but here the denominator looks a little complicated. So we want to change its form to make the denominator easier. Yeah. So we use a standard step. Yeah. So in this situation, yeah. So we know people use this rationalize the denominator. So this step called make the denominator as a rational number. We know rational number, right? Yeah, rational. So here the denominator is a rational number. Yeah. So here we want to rationalize the denominator. How to do it? Yeah, there is a standard technique. Yeah, standard technique. We multiply conjugate. Yeah, conjugate. So what's the conjugate? So 1 plus root 5, irrational number. Yeah, it's conjugate. We look at its conjugate number. That's 1 minus root 5. Conjugate number. Okay? So this fraction, you multiply, you use its conjugate on numerator and a denominator. Both numerator, denominator, you do multiplication. Okay? All right. Yeah. So when you do that, root 5, conjugate. All right. Look at the denominator. 1 plus root 5 times 1 minus root 5. Yeah. 1 plus, sorry, yeah. I think you know this formula, right? Well, a plus b times a minus b equals a squared minus b squared, right? Yeah. Yeah. So here, 1 plus root 5, 1 times 1 minus root 5. 1 squared minus root 5 squared. That's 5, right? Yeah. So negative 4. Yeah. Negative 4. Okay. So then you do cancellation. Yeah. Negative 4. But the numerator 1 minus root 5, it's a negative number. So you switch those two numbers. So then you can, take care of the bottom negative sign. Yeah. So the answer is this. Root 5 minus 1 over 2, the second term. Yeah. Then you have common denominator, right? Yeah. Both terms, you have common denominator. So then, minus 1, 1 cancel out. Yeah. Root 5 plus root 5, 2 root 5, and you have denominator 2, you can do cancellation. Okay? 2 cancel out. So root 5 and this root 5 cancel out, right? Yeah. So after the cancellation, you get a 1. You get a 1. Okay? Yeah. So we complete verification of the second base case. Yeah. All right. Yeah. It should be enough. Yeah. Because if you look at the terms, right, recurrence relation, it's enough. Yeah. Yeah. But here, I like to do a few more steps. You know, try to give you some, you know, experience on golden ratio numbers. Use how to use golden ratio numbers. Give you a little more experience. All right, for step 3, yeah. So this time, well, we need to do this verification. Yeah, although it's not necessary, but we just do some practice here. Okay, all right, yeah. Then plug in, yeah, rational second term, yeah, second term. Say I replace, yeah, because we did the rationalization before, right? Yeah. So here we can jump to that step. Yeah. Then we do expansion. Yeah. So because this time we use the formula a plus b squared formula, right? So you do expansion using this formula, 2ab plus b squared. You use this, apply this formula. Yeah. So the minus version, yeah, you have a minus version, a minus b squared formula. Okay, all right. Then cancellation. Now cancellation, right? So 1 cancel out, the 5 cancel out, 2 root 5 minus negative plus, right? So 4 root 5, but if your 4 cancel out, root 5 cancel out, another 1. Okay, yeah. Yeah. After the cancellation, simplification, yeah. So you can verify that F2 equals, and we know F2, F sub 2 equals 1. Yeah, right? It's correct. Yeah. All right. So we'll verify the first 3 cases. Okay. All right. Yeah. Yeah. Definitely, it's enough for the step 1 here. It's enough. So we do not need to do more. Yeah. All right. Yeah. But here, I like to do another step. This time I will use a different way to do verification. Yeah. Because from the previous step, you can see when you calculate certain power of golden ratio, it becomes more and more complicated, right? Yeah. So people don't like to do that kind of calculation. Yeah. Here, I show you a special way. Yeah. So that, give you some special method to manipulate golden ratio. Yeah. All right. Yeah. Here, let's do one more verification. But this time, we do not plug in the golden ratio number to do the calculation directly because too complicated. Although you can do it, but we don't want to do it in that way. All right? Yeah. So here I want to use the properties of golden ratio to do the verification. Properties. So what are the properties of golden ratio? Okay. Yeah. So here we observe the degree of the golden ratio terms a little high. Yeah. Yeah. Degree 3, although not too high, but we know when the n numbers becomes larger and larger, the degree is higher and higher. That this property makes the computation more and more complicated. Yeah. All right. So the question, the idea, yeah. So how to make it simpler? Yeah. So there is a straightforward idea. We want to bring down the degree. Yeah. Can we do something to bring down, make the degree lower. Yeah, yeah. So that's the place we need to apply certain properties of the golden ratio. Yeah. All right. Yeah. So what properties? Now we need to see those properties. Yeah. Here, there are two properties we can use. One, the first property, 1 equals phi squared minus phi. That's first property. Yeah. How to see it? Yeah. I'll show you. Yeah. But the second property, phi squared equals phi plus 1. There are these two properties we can use here. Yeah. So you may ask, how do you get these two properties? Yeah. Yeah. So we need to recall, how do we find the golden ratio? When we calculate the golden ratio, we'll solve this quadratic equation, right? We solve it. We get a golden ratio. So the golden ratio phi is the root of this equation. So if you plug in the golden ratio number into this equation, you get a equality, right? Phi squared minus phi minus 1 must be equal to 0. You get this equality. Now, so from this equality, can you get these two formulas? You're just using the basic algebraic rules, right? Yeah. So you move the terms from the left to the right, yeah. So you can get the first property, you can also get the second property easily. Right? Yeah. 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 So must be true, these two properties. Yeah. Then we can apply these two properties to help us bring down. So when we have a term regarding the golden ratio, the degree number relatively high, we can apply these two properties to bring the degree down. Yeah. Now I want to show you how to do it when we do our step number 4 verification. All right. Yeah. In this step, first, phi cube. Yeah. So the degree too high. Yeah. Yeah. To bring it down, yeah. Let's split it. Yeah. Phi cube equals phi times phi squared. Right? Yeah. Phi times phi squared. Yeah. Now you have the phi squared term, right? Phi squared term. Yeah. The second property tells us phi squared equals 1 plus phi, or phi plus 1. So you just replace phi squared by phi plus 1. Okay? Yeah. So then multiply through equals phi squared plus phi. After that, you see another phi squared. Another phi squared, so you can apply the second property another time. Replace this phi squared by another phi plus 1. Yeah. So you get a 2 phi plus 1. Yeah. Yeah. Look at the new expression of this phi cube. The degree becomes 1. 2 phi plus 1. Yeah. 2 phi plus 1, the degree is 1. That's pretty low, right? Yeah. That's pretty low. Yeah. Yeah. All right. So that's the first case. Yeah. But second case, yeah, we need to represent 1 over phi cube. This time, the high degree term appears at a denominator. Okay? Yeah. Now we want to bring down the degree number for a term at the denominator. So that's a little harder than the numerator, right? Yeah, denominator. Yeah. Yeah. But the good thing is, yeah, this time numerator is 1, right? The numerator is 1. And our first property gives us a special expression of 1. 1 equals phi squared minus phi. So we can replace 1 by phi squared minus phi at the numerator. All right. So if we do that substitution, you can see after the substitution, both the numerator, denominator, they have common factor. They have a common factor, right? Phi is their common factor. You can do cancellation, cancel out. After cancellation, the degree of the new denominator becomes lower, right? This time degree 2. So you do some improvement. In improvement, you bring down the degree from 3 to 2. Okay, so that's some progress. Let's keep going. So we along this direction, let's keep going. Do one more step. All right. Do further simplification. So here you see another 1. Phi minus 1, another 1. So you can apply the first property another time. Replace this 1 by another copy of phi squared minus phi. Okay. And after some, combining the terms, so you have 2 phi minus phi squared, then numerator, denominator, common factor again. You have another round cancellation, right? So after simplification, you get a 2 over phi minus 1. Now the degree of the denominator is 1. That's pretty good. Degree 1. We should not complain, right? Degree 1. Although if you like, because you have 2 here, 2 times 1, you can do another 1. But, at some point, we feel, it's good enough. So then we do not need to do another round. Okay? So here, 2 over phi minus 1, so we feel it's good enough. All right? Now we're ready to do the final round calculation. Phi cube plus 1 over phi cube. This time, we use our, 2 new expressions. We're adding together. Minus 1 plus 1 cancel out. Gone. And the common factor 2. That times parenthesis phi plus 1 over phi. Inside parenthesis. But we calculated this before, right? Parenthesis. Remember? We calculated that before. All right? All right. Remember when we calculate Fibonacci f of 1? We did it. Okay? So this tells us, this equality tells us, based on we get f3 equals 2 times f1. Because if you multiply left-hand side by 1 over root 5, and you also multiply right-hand side by 1 over root 5, then you get f3 left-hand side, 2f1 right-hand side, like this. Okay? Then you get f3 equals 2. F1 is 1. 2 times f1, that's 2. So you do another verification. Although this step in our standard mathematical induction, this step is unnecessary. But here, I just want to show you how to apply the properties of golden ratios to do some manipulation related to polynomial. So when you need to simplify a polynomial of golden ratio, you can use these 2 properties to bring down a polynomial degree to 1. Polynomial. The degree could be very high, but you keep applying the properties. Yeah, these two properties. Yeah. The second one you use on the numerator, the first one you use on the denominator, to bring down the degree of polynomial at the denominator. Yeah. Okay. Things like that. Yeah. All right. Yeah. So that's the base case. Then next, we need to do the general case. General case. Yeah. So that's the main verification work at the general case. All right. So let's do it. Yeah. Verify the Fibonacci formula. Yeah. So this time we need to see the power of mathematical induction. Very powerful. Right. All right. Yeah. So the first step, we need to check the check base. We already did, right? Yeah. 2 enough. The first 2 base cases enough. Yeah. Second, we need to make induction assumption. All right. So our induction assumption here is, the formula is true. Yeah, because we already know 0 is true, 1 is true, right? Yeah. 0, yeah. So we can add. So this 2 number, yeah. Actually, this 2 number, we can lower it to 0. Okay. Yeah. So replace 2 by 0. How about that? Yeah. So if k is in the range between 0 and n, okay, so this n, yeah, we need to say something about this n. N greater or equal to 1, right? Yeah, because the smallest n is 1. Yeah, so here I want to modify this range to between 0 and n, but n should be greater or equal to 1. That's the range. Yeah, we know this assumption has some base, right? Yeah, yeah. This assumption has some base. Yeah, the base is, the first base case. The first base case is the base of this assumption. Yeah, it has a base, so we can build a building on this base. Yeah, there is a base, so we can start building this building. Yeah. Otherwise, if you don't have the base, how can you build a building? Yeah, yeah. Here we can do the the step 3. Yeah. So under this, in this range, when k in this range, we assume, this fk has this expression. Assumption. You assume it's correct. You assume it's correct. Yeah. All right. Yeah. Yeah. In certain range. Yeah. Because when you make assumption, you should be very careful. You cannot assume too much. More you can handle. That's too much. Yeah. So, yeah. More you can handle. Yeah. Here, if we choose some reasonable range, this is our reasonable range, then we can handle. Not too much. Yeah. In this range. Yeah. And in this range, yeah. This range between, in this interval, that's the range. Okay. And we know n greater or equal to 1. Yeah. And we know the smallest range. The smallest, that range. Yeah. There is something. Okay. Yeah. The range is not empty. Yeah. There is something there in the range. Yeah. So when we start, this is our smallest range. Yeah. The next question, can we grow our range? Yeah. If we cannot grow this range, then we have no gain. Okay? Yeah. No gain. Yeah. You can not get anything. Yeah. Yeah. So our plan is we want to move this range from 0 to 2. Next step. Then enlarge this range. All right? Yeah. Keep enlarging the range. Eventually, our range covers all the natural numbers. Our range can cover all the natural numbers. How about that? Then we are done. Okay? That's the idea. Yeah. So our step number 3, we need to show we have the capability, we can enlarge the range. You have that capability to grow the range. Then you get a whole statement. All right, so that's the critical step. Yeah. Step 3, we verify that F, this formula, we do verification. We need to show it's correct. We need to show this new formula. Yeah. All right? Yeah. Because if you look at the subscript, this time k equals n plus 1, that's out of the range, right? Yeah. So this k out of the range. Out of the range from 0, this interval, range interval. Okay? Out of the range, that means at the left-hand side, when you calculate f sub n plus 1, you cannot use induction assumption, right? You cannot. Yeah. Because k falls out of the range, your assumption cannot be used anymore. Out of the range. Yeah. All right? So how do you represent f sub n plus 1 at the left-hand side? You can only use the original recurrence relation. Original recurrence relation always true, right? Yeah. Everywhere, if you like, you can apply the original recurrence relation. All right? Yeah. So here, let's do formula transformation. Yeah. All right. So this time, left-hand side, yeah. Yeah. We can use the, yeah. So left-hand side, yeah. So we apply the original recurrence relation. So this step is legal, right? Yeah, it's legal. Yeah. Okay. Yeah, it's legal. Then after we apply the original formula, the next time, yeah, because now the subscript becomes n and n minus 1. Yeah, and let's recall the range. Range in our assumption. If k subscript k falls into this range, then we can apply our induction assumption, right? Yeah. Now the subscript k, the first time it's n, so we can apply induction assumption. It falls into the range. Yeah. So it's legal to apply our induction assumption. Then the second term, this time the range k is n minus 1. N minus 1 falls into the range, right? Yeah. So we can apply induction assumption on the second term. Yeah, let's plug in. Yeah. Legal, both legal, right? Both legal. All right. Now we need to do the verification. So this whole thing is our f and so on. So can we show this whole thing in this expression equals our targeting form? So this is our targeting form. We target that form. Okay? If we can show these two expressions are the same, then we are done. Two expressions, they are the same. Yeah. So we complete our verification step. That's the logic. Okay, all right, yeah. So let's do that final step. Yeah. So we simplify. Yeah, this formula pretty complicated. So let's take out 1 over root 5. So inside parentheses, we have 4 terms. Yeah, all right. And we compare it with our targeting form. Yeah. Both of them have the same 1 over root 5 constant multiplication in front of that pair of parentheses. So we can ignore that same constant, right? Yeah. So we only need to show the part inside parentheses are the same. That's enough. Okay, that's our, new verification target. Okay, all right, yeah. So let's show that. But in our new verification target, yeah, the formula is still quite long, right? Yeah, formula is still quite long. So now we do another round processing. Process our information, the information we have. So we do observation on these formulas. So you can see the formula at both places, they have some property, special property. Okay? If you look at the structure, the structures of these two formulas, you can see they share some common properties. Yeah, what's that? So when you look at this formula, there are 2 terms. Yeah. The first term, so we split 2 parts. Yeah. The first part, the term phi, it's a monomial form, right? Yeah. Phi to the n. So it's a monomial form. Okay. The second term, fractional, in a fractional form. First term, integral form, right? Integral form. Second, fractional form. Yeah? Here, you can see you split into 2 parts. The first part, integral form, right? Second part, fractional form. Yeah. So if you compare these 2 structures, you can see it's reasonable to make this kind of connection. Their corresponding integral parts should be the same, and their corresponding fractional parts should be the same, right? Yeah. Yeah. Because when you compare the structures, they have the similar structures. Yeah. Yeah. So the structure is important. When we work on the formulas, the structure is very important. Yeah. Here, so now this is our imagination. Okay. Yeah. Because when we do the formula processing, yeah, our imagination is very important. So here, yeah, so our new target. So this is our new target. Okay, yeah. New target. Okay, and the fractional part should be the same. Yeah. Yeah. So we split 2 parts. Yeah. Can we verify these 2 equalities? If we can, then we're done. Okay? Yeah. So our current goals, we need to verify these 2 formulas. Yeah. All right. Yeah. So let's do it. Yeah. All right. Yeah. So when we do the verification, yeah, we know this is correct, right? This is our starting point of the verification. Okay. All right. Yeah. Then, yeah, we multiply same expression, phi to the n minus 1, both sides. Yeah. Then you get it. You get our first target, right? Yeah. First target. Yeah. Simple. Yeah. Simple. Okay. Yeah. So verification of the first one, very simple. Okay. All right. Then The second one, a little harder. Yeah, so second one, we need to do more work. Yeah, all right. Yeah, but for the second one, our second target, this one, to show that, we use one special way in problem solving, commonly used method. That's called backward thinking. Backward, because this is our goal, right? This is our target. Yeah, this is our target. But backward thinking is we think backward. We assume we have this target already. Okay, yeah. We start our deduction from our goal. Okay, from the end point. That's our starting point. Then we do the backward deduction. Okay, all right. If this is correct, what can we get? Yeah. We remove the common denominator, right? So we'll multiply the common denominator both sides. After we eliminate common denominator, we get this new form. One step deduction. So backward. Okay, all right. And the step of this deduction is two directional, right? Yeah, both ways. You can if this is true, you can go that direction. Yeah. Okay. So both ways correct. Okay. Yeah. Later we will use the other direction. Yeah. All right. Then we need another step deduction, simplification. Yeah. Because this -1 to certain power quite annoying, right? Yeah. Not very friendly. Yeah. Make the formula more complicated. So our next round simplification, we want to remove the -1 power. Okay, all right. How do we do it? We multiply this -1 to the n-1, that power number. Okay, after modification, the left-hand side becomes 1. Yeah, because n plus 1 plus n-1 is 2n. Yeah, -1 to the 2n, that's 1. Okay, yeah. Then after simplification, you can see you get n squared, right hand side n squared minus n. Yeah, because you look at the exponent number of -1, where it is an odd number, you use -1. Even number, you use +1. Okay, yeah. So when you do that, odd number, even number. So for this term, even number, exponent even number, so you get a positive coefficient, phi squared. For this term, you get a exponent exponent number, odd number, so you get this -1. Okay, yeah. So you end up with this one. Is this our first property? First property of golden ratio, phi, right? That means it's true, right? Yeah, it's first property. That means it's true. If it is true, can we go this direction? Yeah, because both ways, right? Yeah. These equalities are true. We can go both directions, both ways. Yeah. Now we go this way. Yeah, because it's true, we go this way. Then go that way. So we get our target. Okay, yeah. Starting from the first property of golden ratio, we do the, deduction, forward deduction, right? This time we do forward deduction, so we can get to our second target. Then our verification is done. It's done. Yeah. So by the mathematical induction, yeah. So we verify the step. Then our final conclusion, we have shown the whole Fibonacci formula is correct by mathematical induction. Now you can see why we say it is so powerful, mathematical induction. It's powerful. Okay? Yeah. All right. Yeah. Yeah. So we completed verification. Okay. All right. Yeah. Yeah. All right. So we finished this topic. Yeah. Then our last topic, D.3, linear recurrence relation. Yeah. So remember, we need to discover the Fibonacci formula. Yeah. So the goal of this topic, we need to discover the Fibonacci formula. Okay. You cannot assume you already know the formula. In the real world situation, you cannot assume you know the final result, right? Yeah, that's too much. Yeah. So in the real world situation, you need to discover the new result. That's the hard part. Yeah. Because the discovering step, always the hardest step. Verification step, much easier than the discovering step. Yeah. So we need to do the step. Yeah. Yeah. But here, yeah, because to complete this topic, I need a little more time. So here I do not have much time. Yeah. But I plan to do one small topic. Yeah. I can complete within 5 minutes. Okay. All right. So that topic is, yeah, here. I want to do one special thing. Yeah. Yeah. I must complete in 5 minutes. Yeah. So what's that? Yeah. Last time, yeah, one student, Gabrielle, she asked me to give more examples, right? Solving the, targeting the, especially for the challenging questions, right? Yeah, more examples. Yeah. So I want to, try to help you do preparation for the final. So right now, we need to do preparation targeting the final. Okay. All right. So I got inspiration from her suggestion. Yeah. So I plan to do it this way. Okay. So here today, I do the the first round. Yeah. First. So yeah. Today I do this. FBR1. F means final. Okay. Yeah. Now we do preparation for final. B R basic result. Yeah. So when I do this example I treat as the basic results. So in the final, yeah, these are basic results. They are the results we can use. So I try to build a list of basic results you can use for the final. But when we build, they are our examples, right? They are the examples you can study. Yeah. All right. So the first example, because very simple, so I can complete quickly. Now, when we start, okay, the first example is find the median of 3 elements. Okay, yeah. That's a simple question. Yeah. Yeah. 1, 2, x 3. Okay. That's the first example. All right. Yeah. Because in my grading, I noticed many students had the problem. When they do that, they give me the best case. Yeah. Here, we need to do it for the worst case, not the best case. Okay. We always, work on the best case. Yeah. But so many students give me the best case. Okay. That's not good. Okay. All right. Yeah. So here, yeah. Yeah. So the answer is 3 comparisons, not 2 comparisons. Yeah. Many students give me 2 comparisons. That's the best case. Okay. All right. So first comparison, First comparison, that's easy, yeah, because let's just compare x1 and x2. Okay, all right, and assume x1 less than x2. Okay, this step we know without loss of generality, right? Yeah, without loss of generality. Okay, yeah. Then the next step, second comparison. Okay, so you have two choices. Yeah, so here, if we draw diagram here, yeah, because now x2 higher, x1 lower, you have a point x. So you have one comparison between x2 and x3, another comparison between x1 and x3, right? Yeah, either one, similar situation. Yeah, so you just pick one of the two. Yeah. So here, let's say we compare x2 and x3, all right? x2 and x3, all right? Then, two possibilities, right? Yeah. The first possibility, x2 less than x3. The second possibility, x2 greater than x3, all right? Yeah. All right, but for the first case, we have the result, right? The first case, yeah, because this case means x1 less than x2 less than x3. x2 is the median. Yeah, let me finish quickly. All right, yeah. But the second case, we don't know, right? Yeah. So the second case, we do not know it. Know it. Okay. That means this case should be the worst case, right? Because the first case is the best case. Okay. So we should assume this case. Yeah. Assume x2 greater than x3. Yeah. Because we target the worst case all the time. That's why we need a third comparison. The third comparison, yeah. Third comparison, yeah. Because x2 is the maximum, right? So this x2 equals the maximum. Okay. Third comparison, not here. Third x1 and x and x3. And we know the larger one is the median. Okay. Yeah. All right. So we complete our first final basic result. Okay. Yeah. So I try to collect. Okay. Yeah. Every class, I try to do one or two. Okay. Examples like this. So let's build up for our final. In the final, you can use these results directly. Okay. If we have 10, 12, 20, you just use these results directly. Okay. Yeah. Just like your dictionary. Okay. Yeah. Your formula list, use it directly. All right. That's it.